This webinar has topic from PSDM Velocity Cube to reliable 3D velocity model. Seisquare has been applying this technology in a number of operational projects in past couple of years with really compelling results. And today we are very excited to share this case study and the theory laying behind it with you. Our presentation will last 30 minutes. My colleague, Luc Sanjeevi, CTO of Seisquare, Mikhail Kali, Senior Geophysicist, and me, Victoria Bilan, Technical Marketing Manager, will make a 20-minute presentation. And we will open the floor remaining 10 minutes for your questions. Luc will start the presentation.
Hello everybody, I'm very pleased to have you on this session this morning. This is the second webinar we hold on the PSDM seismic velocities and their use for depth conversion. Some of you have maybe attended the first one where we just focused on the case study where we had a before-after picture where we showed that without a proper conditioning of seismic velocities, you could have some failure in depth conversion, and after seismic conditioning, data conditioning, it was much better. And in this webinar, we start with the same data, but we focus on two main things: the workflow from the seismic velocity cube to the condition and calibrated velocity model first, and with a spatial focus, of course, on the spatial data conditioning with a simpler explanation by Victoria. This is the workflow we are talking about. We start from the PSDM velocity cube and the seismic time interpretation. We perform this, the technology spatial data conditioning. We output the condition seismic interval velocity map and the time maps, plus of course the calibration of the quantification of the uncertainty. We input the well markers, and all the stuff is in our engine for depth conversion, the UDO plugin for Petrel. The output is calibrated to the well for calibration to the well for interval velocity map 2D and 2D depth map, plus of course the confidence interval. And from these outputs, we rescale them in 3D to end up with a 3D reliable velocity model that is conditioned, calibrated to the well, and usable for depth conversion or inversion. So this workflow now will be showcased by Mikhail on a real case study on Petrel, and then Victoria will come back on the spatial data conditioning more precisely.
Let's set the scene and have a bit of context in this study. We have 4 different layers in this study with 7 different wells that we control, and 1 well of exploration, but it's not really, in fact, during the real study. It's 4 kilometers away from a control well. We have, so in this section, you have the 4 different layers: the seabed, a shallow layer, and 2 layers that define a salt interval with very poor seismic characters. And the target horizon is below this salt interval. You have the existing well, the only one that is reaching the target horizon, and you have an exploration well that is just below fault. In this case study, we will have 2 different velocity model scenarios for depth conversion. One that we will take PSDM velocity for granted, and the second one with spatial data conditioning that we will apply on PSDM velocity. So before after picture is here on the section. You are when you take PSDM velocity for granted 245 meters off target when you are looking at the estimated depth and outside of the confidence interval, and you are after spatial data conditioning on the estimated depth just only 40 meters off target and in the confidence interval. So I will present you now all the workflow that Luc has presented before, but on Petrel. Here we start with the velocity cube, the raw velocity cube. You can play with it, have a little look at it. Here are the data. See a little about velocity with a different change due to the layer model. We can see after the different time interpretation that we'll use for the conversion of the seabed, the second horizon here, third one, and the target horizon. From this interpretation and the raw velocity cube, we'll extract the different interval velocity. And it's what we have here, different raw interval velocity. With this data and the time interpretation, the interval velocity extracted on all the horizon, so wet depth marker, we'll enter to UDOMO depth to do the time to depth conversion. Scenario 1, we have here on UDOMO depth. So using Bayesian cockrigging, UDOMO depth integrate all sources of depth conversion uncertainty simultaneously throughout all layers with a unique probability model. The software best estimates the velocity model parameters by minimizing wide depth matches and offer interactive graphic control. For more explanation, we have an explanation of the approach on our website. Just to show you, the interface is quite similar to make velocity model. You enter your different time interpretation for 4 different layers. You will choose your velocity model. You have the parameter here, and here you enter your different original or velocity. If we run this model, we arrive to this depth at the target horizon. What you see is that we are tied at the well, and here you have the exploration well. The problem is when we are looking at the depth, the actual depth of the exploration well, we are 245 meters above when you are looking at the estimated depth. So what is the problem here on the conversion? The well depth marker are okay. The time interpretation also have been checked. The velocity model is quite good with no remaining too much depth matches. The only thing that remains unquestioned is the seismic velocity that we enter in this interval in this velocity model. So we have applied the spatial data conditioning on the different seismic interval velocity. Here is the result of this spatial data conditioning. Here for the first layer, the raw velocity, or after the condition one, see that we have quite a change between the two one, and here are the velocity artifacts for the first layer. Second layer, it's more impressive, with a lot more artifact, and notably something that is maybe due to a fault shadow. And for the target horizon, here, so before, after picture, it's here with the velocity artifact. So with all this conditioned velocity, we will enter to a second scenario in UDOMO depth. We have exactly the same kind of scenario. We have just replaced the first layer with a constant velocity because always seismic velocity in a velocity cube are not reliable. So I just put a constant velocity, but after we use all conditioned velocity for the different layers. With UDOMO depth, we apply new calibration on this velocity, that leads to minimize depth matches, and we can run this new model. So the results are here. See that it's maybe quite different from the first scenario, but we are still tied to the well. And most important, the exploration well is not so far from the estimated depth. Compare it to the first scenario. See that the structure are not quite the same shape, and also we have big difference on the velocity that is resulting from this conversion. So first case and the condition case, and if we show it the raw case, here the velocity. See that we have quite a rough change on the resulting estimated interval velocity. Now, we have applied this spatial data conditioning. We have done even in multi-layer, it's a multi-3D conversion. We have now to apply all this correction in 3D. Let's go back to the original seismic velocity cube. Here. Here's the original seismic velocity cube. And here is the application of the correction on the seismic velocity cube that we apply in 3D. So from a first velocity cube, the raw velocity cube, we arrive to this one that can be used for depth conversion. I have now presented what we achieved here for this study. Victoria will explain you what is behind the theory of spatial data conditioning.
Thank you, Mikhail. I hope everyone understood how to go from PSDM seismic velocity cube to 3D reliable velocity model. And now let's focus on spatial data conditioning. What is it, spatial data conditioning? SDC is about best estimating the spatial components from seismic velocity data sets that contribute to depth conversion, and about filtering out the spatial components that are considered irrelevant for depth conversion. The algorithm which we are using in spatial data conditioning is factorial kriging. So, what is it, factorial kriging? Factorial kriging is about decomposition into independent trend residuals, spatial components of a given regionalized variable. It means that regionalized variable could be split into spatial trend with a low spatial frequency non-stationary and into spatial residual with a mid and high spatial frequency stationary. At the same time, it means that spatial trends is given as a shape factor, while spatial residual is given as a covariance model. If you need more advanced information about factorial kriging, you can go to free ebooks by IFP, Energy Novel, and Seisquare, which are published on our website, seisquare.com. In geophysics, we apply factorial kriging as the composition of seismic interval velocities. It makes possible to split PSDM seismic depth is opaque into PSDM structural depth seismic is opaque corresponding to PSDM consistent seismic velocity, and into PSDM artifact depth is opaque corresponding to PSDM artifact seismic velocity. Here you can see a clear illustration that PSDM seismic depth is opaque is split into PSDM structural seismic depth is opaque and into PSDM artifact seismic depth is opaque. In other words, seismic depth could be split into seismic depth trend, which is given as a shape factor function of the seismic time, and into seismic depth residual, which is given by a variogram of the seismic velocity residual. From secondary school, we all know if we divide the depth by time, we get velocities. So, the same operation we do here. We divide PSDM seismic depth is opaque by seismic time is opaque. And consequently, we get PSDM interval velocity fields. We have PSDM interval velocity, which consists of PSDM velocity which are relatively high in red and relatively low in blue, and we also have PSDM artifacts related to high and low velocities. This PSDM interval velocity could be split into PSDM consistent seismic velocity, which is correlated with seismic time is opaque. As in your data set, you can see that when we have PSDM velocity which are relatively high, our seismic time is opaque is thin, while when our PSDM velocity is low, we have our seismic time is opaque thicker. In contrast, PSDM artifact seismic velocity is not correlated with seismic time is opaque. We clearly see that PSDM artifacts related to high and low velocity doesn't impact seismic time is opaque. So, is it possible that actual interval velocity is not correlated to seismic time? No. PSDM artifact seismic velocity are just lateral seismic velocities variations inside the layer which are generated by the PSDM seismic processing. It means that PSDM artifact seismic velocity is not correlated with seismic time is opaque, and we should ignore this PSDM artifact seismic velocity for depth conversion. Here we can clearly see what Mikhail Kali was doing in Eudomorp trail. He splitted PSDM seismic average velocity into PSDM consistent seismic velocity variations and into PSDM artifact seismic velocity. Here we can have a proof that PSDM artifact seismic velocity is not correlated to PSDM seismic vertical time. If we get a closer look into PSDM artifact seismic velocity map in the black zone, there are some variations, while in PSDM seismic vertical time, there are almost no variations. This proves that there is no correlation between two maps.
Let's back to Petrel. You have seen a bit of theory around spatial data conditioning of the velocity. Now we'll go back to the conditioning here and focused on the first layer conditioning, because here in this first layer we can possibly see the effect of this conditioning on the well, because here you have the 7 wells that are reaching this layer. So if we look at the cross plot between well interval velocity versus raw seismic velocity, you can see that in the first case we can have a regression, but it's not really good. And after conditioning, we have a better regression, and we can use in a better way the seismic velocity. The thing is, on most of the study, after conditioning, we tend to have a regression for this slope. It's not maybe better, but always tending to 1, meaning that you have more geophysical meaning in this velocity, because you only need a calibration on this velocity to pass the seismic velocity to an interval velocity. And if we go back to the correction on the velocity cube, if we look in particular at this first layer, you can see the impact of the conditioning between the two velocity cubes. I will change the color scale. Here is the original velocity. And now the new one. See the difference before, after. To conclude this webinar, I will say that taking PSDM velocity for granted in the context of depth conversion can lead to a biased depth map and a wrong ENP decision. After SDC, the contributive part of the PSDM velocity are consistently identified, leading to more accurate and reliable depth conversion. The reason why PSDM velocity are relevant for depth conversion after SDC is that they are fully consistent with time interpretation. In the workflow today, we bring you from a 3D seismic velocity cube to a reliable 3D velocity model. It's here the end of this webinar, and we are now open to questions. So Larry is asking, does the type of PSDM input, and for example, what if the PSDM velocity have anisotropic correction already?
Okay, of course, this workflow will run on, I would say, any time of seismic velocities, but the performance is depending, of course, on the kind of PSDM velocity. Usually, I think the most relevant use for the workflow is, well, the best result we have is with anisotropic PSDM processing. And even well, and this, the best thing would be that the PSDM processing is even tied to the well from the start. Okay, if the anisotropic coefficient in the PSDM takes the well into account, then they are tied to the well, and you cannot see anything from the correlation from PSDM depth to the well depth because they perfectly fit. But what is the guarantee that outside the well area you can trust the PSDM? This is where this workflow is the most efficient. This is where you can highlight PSDM inconsistency that cannot be that are corrected, I would say, through the anisotropy coefficient at the well. So I would say yes, the workflow applies on a number of cases, on a number of PSDM processing. The best result we have is on the anisotropic processing when the PSDM are nearly tied to the well, but we have no clue on their consistency outside the well. Michael, we have another question?
We have a second question. It's from Helmut. The quest of the structure after conditioning seems to be shifted away from the exploration well. Does that make sense?
It looks like in this area that we are facing a quite strong fold shadow effect. So the velocity field that I think that the interpretation they had of their prospect, it was below salt, was wrong at the beginning, because they trusted on the left hand side, what you see on the left hand side, a quite good prospect, when in fact after the correction of velocity, the structure, the geological structure is changing nearby these faults, and we don't know, because we don't. Well, let's say I would say that we would have to trust the depth after conditioning, but the truth is that, of course, although we have a very good fit with the exploration well, you see that the exploration is perfectly fitted, only 40 meters difference with this new depth. The guarantee that the shape of the prospect around is exactly this one, I think that we are lacking something. We would have liked to have the opportunity to rerun migration iteration using the new velocity field. And this is what is missing, I would say, in this workflow, but we usually have no way to go back to processing at this time. What we think is, now that we have the possibility to go back in 3D, rather than applying a vertical depth conversion after the SDC of velocity, it would be better to rerun migration iteration, just ray tracing, so to take into account the possible impact on the depth structure. But yes, in this means that you cannot trust your prospect when you are in heavily faulted area, where the PSDM shows you on the left-hand side a structural pattern that you trust, and when you look at the PSDM velocities underlying this pattern, you see that a new pattern appears, which is much more consistent in terms of depth. So the final answer is, well, in terms of depth, we are much more accurate at the target, or at the target well. The recommendation would be to rerun PSDM iteration to have a better migration and positioning of the events, rather than a depth conversion, vertical depth conversion with the initial time that might have changed after a new migration. But that's unfortunate, but today it's very difficult for, I think for you too in the company, to have access to the contractor once these PSDM data are available.
Thank you very much, everybody, for your attendance. I hope you enjoyed it, and our team is always available to answer any question regarding technology we presented today, or to organize individual WebEx with your team. And looking forward to meeting you on our next webinar.